Okay, so now we're going to use the curl for practical purposes, meaning in order to determine if a vector field is conservative or not. So remember, if you're given a vector field f, the curl of f, sometimes it's written this way, but it's more convenient to write it in this way because it's easier to memorize what's going on. This will be a new vector field, so it will have new components, and the way to remember which components go in each entry is that you can use the same notation. You follow this is why you use the notation of cross product, because in many ways it behaves like a cross product. So the trick for memorizing the formula of the cross product was to use the determinant of the 3x3 matrix, where you put ijk in the first row. In the second row, in the third row, you would put the entries of the second vector, and in the first row, this is strictly speaking not a vector, but you just put like the partial derivatives with respect to each of the coordinates. And the main result, like here's a trinity of holy trinity for vector fields or conservative vector fields, is that f is conservative. And again, strictly speaking, sometimes you have to be a little bit more careful with this statement, but not for our purposes. So f is conservative will be the same as saying that the curl vanishes. And this is a new thing, here's a trinity. It will be the same as saying that f admits a potential. And so let's use this in practice so that you see how this works. Let's say you want to determine, so question, let's say you have this vector field f, so I give you this vector field. At the point x comma y, you have to draw this vector. And the question is whether or not that's conservative. So checking if something is conservative, the easiest way to do that is just computing the curl. So what's the curl of this vector field? Again, you use this formula that I have here. And then you compute this in the same way in which we were computing cross product. So you do this along the first row. When you do the first row, you get the partial with respect to y of cosine of c, which is 0, minus the partial with respect to z of negative c, which is just 1. And then in the middle, you get 0, you get 0. And in the last one, you get 0, and you get 0. And so the curl of this vector field is just 1, 0, 0. But that's not the same, so that's not identically 0. You need all the entries to vanish on the nodes. So this is 1, 0, 0, which is not conservative because it's not the vector with just zeros. Okay, so this is a cool tool to check efficiently if something is conservative or not. Let's do another question, which is how about the following vector field? So let's ask whether or not yx4. So the next question is whether or not this is conservative. So again, let's try to compute the curl one more time. So the first entry goes, you get 0 minus 0. The second entry you get, well, this will be 0, 0, so you get 0. And the last entry you get 1 minus 1, which is 0. So the curl is 0 in this case. So that implies that f is conservative. And because of our triad, that means that you can find a potential for it. So let's try to find a potential. So remember that f admits a potential, which in practice means that you can write f as a gradient of some function that gave you a system of equations, right? Remember, this is the same as saying this gives you 3 equations. And so, again, you just start solving it, but solving the equations by doing like partial integrals. So if you start with the first one, you have the partial of v with respect to x equals y. So you integrate with respect to x. Again, this is like yx because this is a constant. Y is now a constant. There's a constant integration because you're doing like an indefinite integral. But this constant of integration now depends, since x is the only variable in this case, this constant of integration depends on y and z. Okay? And now you substitute in 1 and 2. Sorry, 2 and 3, which are the 2 equations we haven't used. So the equations become the partial of v with respect to y, which is x plus the partial of z with respect to y equals x, and then there's this new second equation. And the new third equation is that the partial of v with respect to z, which is just this thing, has to be 4. And again, now you just take whichever you prefer. So if you take the second one says that x is on both sides, so that says that partial of y with respect to the partial of z with respect to y equals 0. So again, what does that mean? It means that this was a function of y and z. So if the partial derivative with respect to one of the variables equals 0, that means that this function only depends on the other variable. So that means that z equals actually a function of y of z exclusively. And so again, you use that to update your potential function, which now becomes yx plus z of z. And now you go to the third equation, and the third equation says Now we know that it only depends on Z, so you can write it this way. And that gives you the Z equals 4Z. Plus, now this is like an honest constant. So updating your potential one more time, this tells you that V of X, Y, Z is Yx plus 4Z plus big C. Okay, and now again, this is a potential for F, because if you took its gradient will be Y x4, which was a vector field we started with.